Today, we're cracking open a case file on one of the biggest construction projects on the entire planet. Yep, this is a geological detective story, and we're on a mission to figure out what incredible forces built the Andes Mountains. So, grab your magnifying glass, let's dive in. First things first, just take a second to appreciate the sheer scale of this thing. The Andes aren't just a mountain range, they're the literal spine of South America. We're talking almost 8,000 kilometers long, stretching down the entire western edge of the continent. This one feature shapes everything: the weather, where rivers flow, even how life evolved over there. It's absolutely massive. So you gotta ask, right? Something this huge doesn't just pop up overnight. It's the result of unbelievable power working over an almost unimaginable amount of time. And that's the big question for us today. What kind of engine could possibly build something on this scale? Well, to find the answer, we have to look deep, deep down. Our first clue takes us to a powerful engine churning away beneath the surface, one that's been reshaping an entire continent for hundreds of millions of years. This is the prime mover in our whole story. And that engine is powered by a process called subduction. So picture the Earth's surface as this giant cracked eggshell made of huge rocky plates. When a heavy, dense oceanic plate smashes into a lighter continental plate, well, something's got to give. The oceanic plate always loses, getting forced to dive or subduct underneath the continent and sinking back down into the Earth's hot mantle. And here are the main players in our case. Out in the Pacific Ocean, you've got the Nazca Plate, and it's chugging eastward. It is on a direct collision course with the South American Plate. And in this tectonic showdown, the denser Nazca Plate does exactly what we just described. It takes a nosedive right under the continent. Now get this, you might think of geology as being super slow, but this whole process is happening at about 6 centimeters per year. Now that might not sound like a lot, but it's about the same speed that your fingernails grow. It's a constant, relentless push that never ever stops. Okay, now take that constant push, that fingernail growth speed, and multiply it by the time involved. This slow motion collision has been going on for more than 200 million years. Can you even imagine the incredible amount of pressure that's built up over all that time, focused on this one single spot? So, we found our engine, a 200 million year long tectonic pileup. But how exactly does that build mountains? Well, it all comes down to what happens when you squeeze a continent for that long. All that pressure has a few big effects. First, the edge of the continent gets squished, crumpled, and thickened, kind of like a rug you push up against a wall. Geologists call that crustal shortening. Meanwhile, as that oceanic plate dives down and melts, hot magma rises up, basically injecting new rock into the crust from below and feeding huge volcanoes on the surface. And finally, all that squeezing bends and breaks massive chunks of rock, stacking them on top of each other into these enormous mountain ranges. And you don't have to take my word for it. You can literally see the evidence written into the landscape. The Andes are really two distinct ranges. The Western Cordillera, that's a classic volcanic arc, full of some of the world's highest volcanoes, all fed by that rising magma. But the Eastern Cordillera is a gigantic fold and thrust belt. It's the crumpled rug part of the story, made from all that intense continental squeezing. Okay, so, case closed, right? Subduction squeezes a continent, you get mountains. Seems simple enough. But, like any good detective story, there's a plot twist. See, when geologists looked at the rocks, they found something weird. The Andes didn't grow at a nice, steady pace. Instead, the whole building process seems to happen in these dramatic, intense bursts of growth, with long, quiet periods in between. For years, this was a huge puzzle. What could possibly cause a planet-sized construction project to hit the gas and then slam on the brakes? Well, the main suspect is this weird variation called flat slab subduction. So sometimes that diving oceanic plate doesn't just plunge steeply into the mantle. Nope. Instead, it travels almost horizontally for hundreds of kilometers, scraping right along the bottom of the continent before it finally decides to sink. And as this recent study points out, it's all about that changing angle. When the slab is flat, it creates way more friction. It basically sticks to the continent above it, transferring a ton more stress. And that's what kicks mountain building into overdrive. Then, when the slab's angle gets steep again, the pressure eases off. So it's not the speed of the collision that matters most. It's the angle of the dive. So that's the theory. But how in the world do you prove it? I mean, how can you know what a tectonic plate was doing millions of years ago? Well, this is where the real forensic geology comes in. finding clues locked away in the rocks themselves. To a detective, a map like this is basically a map of the crime scene. To us, it might just look like a colorful mess, but to a geologist, every single color and line is a clue. It tells them about the different kinds of rock, where the faults are, where things got folded. It lets them rewind time and reconstruct how giants like Aconcagua, the highest peak in the Americas, were built. To figure out the timing of these growth spurts, scientists zeroed in on key evidence, like old rocks made of cemented together pebbles that eroded from the early mountains. And they have this incredible tool that uses tiny crystals called zircon. These things are amazing. They're nearly indestructible, like little geological time capsules. And here's the kicker. Their chemical makeup is a direct record of the pressure and therefore the thickness of the crust when they were formed. So by studying zircons of different ages, scientists could literally measure how thick the crust was way back in time. And what they found in this region was just stunning. 38 million years ago, the crust was a pretty normal 35 kilometers thick. By 12 million years ago, it had bulked up to 44 kilometers. But then, the growth just exploded. In only the last 12 million years, it's jumped to its current thickness of 55 kilometers. Think about that. More than half the mountain's modern height was built in what is, geologically speaking, the blink of an eye, a truly dramatic pulse. So the evidence is all in. We've got our mechanism, we've got the plot twist, we've even got a timeline for the growth spurts. We've cracked the case. But the final verdict reveals something really profound about the world we live on. And the verdict is this: the story is not over. Not by a long shot. This whole process of mountain building, it's happening right now, as we speak. The Nazca Plate is still diving. The continent is still getting squeezed. The Andes aren't some ancient ruin. They are an active construction site. And that leaves us with one final mind-bending thought. The incredible forces we've looked at today are just as active as they've ever been. This isn't history, it's the present, and it's shaping our future. If we could hit fast forward and jump ahead another 50 million years, what would this colossal, still growing mountain range even look like? The geological story of the Andes is still being written. One earthquake, one eruption, 1 centimeter at a time.